Dear ladies and gentlemen, we are all welcome to the second lecture of Eeen202, that is electronics measurement and transducers. In this segment, we are going to continue our discussion on intrinsic semiconductors. In the previous class, we have said semiconductors are divided into two. The first one, intrinsic semiconductors, which are pure, and we did not have any impurity to them. Then the second one, we said they are called extrinsic semiconductors, which are impure in such a way that other foreign elements are introduced into the pure group for elements. And you can remember that we discussed when the temperature started rising to room temperature, the bonds start breaking in the pure semiconductors. But we have established that the average number of bonds that break per mole is 10 raised to the power 11. Dividing it by 10 raised to the power 23, which is approximate value of our Avogadro's constant, we get 1/1 trillion, which is very, very insignificant. So because of that very low amount of charge carriers produced as the temperature rises, we said this amount of current produced is very, very small and it cannot serve the purpose. So in order to increase the amount of current in these semiconductors, we introduce small impurities into the crystal, that's the pure semiconductors, and the process of introducing that impurity is called doping. If you introduce pouring materials into the pure semiconductors, you do doping, and by doing that you are increasing the conductivity of the semiconductor devices. And we should know that whenever these impurities are introduced into the pure semiconductor, it is now called impure semiconductor or extrinsic semiconductor. And whenever you do this doping, we should know that more valence electrons than originals, that is if you introduce, like, let's say group 5 elements. If you take group 5 elements, they have what? 5 electrons in their outermost shell. So when you dope them into group 4 elements, what will happen is that they will share 4 out of their 5 electrons with the 4 neighboring pure semiconductors, which can be silicon or germanium. And after sharing, they have an excess electron which is existing without any bonding. And for this reason, we call this group 5 element as donors. But if you introduce group 3 elements, they have only 3 valence electrons. When they enter the crystal of the pure semiconductors, they will share 3 of their valence electrons, and still they need 1 to share with the 4th one. So because of lack of additional 1 electron, they are called acceptors. And as I've already said, the donors are group 5 elements and the acceptors are group 3 elements. And whenever you dope a semiconductor with donors, that is with group 5 elements, it has excess electron, and the type of electron charge is what? Negative, and that is what we call an M-type semiconductor, that is negative type semiconductors, because they have more electrons than the normal pure semiconductors. And for this reason, since I have excess electron, even if no bond is broken, we said we have electrons as our majority carriers. And when the bonds are broken, the pair of electrons and what holes should be produced. So therefore, the number of holes in any condition should be less than the number of what? Electrons. So that's why we call the holes minority carriers. But if you dope a pure semiconductor with acceptors, that is with group 3 elements, now there is lack of 1 electron, as I have already explained. And wherever electron is lacking, we have a hole. So therefore, the holes are in excess, and for this we call it p-type semiconductor, that's positive type, because a hole has a positive charge. And in this case, before any breakage of bonds take place as a result of temperature or electric energy, the holes are existing. That is why we say they are majority carriers in what? P-type semiconductors. And the electrons, they are the minority carriers. They are only created when the bonds are broken. And for us to understand this, let us look at these 2 diagrams. This one, this is a group 5 element introduced into group 4 pure semiconductors. Now it will share 1 with this, 1 with this, 1 with this, and 1 with this. It shares 4 out of 5 electrons. and still we have one additional electron existing that is not bound to anybody or any atom. So for this we say it has excess electrons, and that's why we call it n-type semiconductor, because electrons have negative charge. And if you come to this one, this is a group 3 element introduced into the pure semiconductor. It will share one electron with this, one with this, one with this, but it has only 3, therefore it can share with the fourth atom of the pure semiconductor. So where the electron is missing, we have a positive charge and we call it a hole, and that is why we call this one p-type semiconductor. And what are the types of the group 5 elements we can use as dopants, that's as impurities into the pure semiconductors? They include phosphorus, arsenic, bismuth, and antimony. They are all used as what? Donors, because they have 5 valence electrons. And the group 3 elements that are used, we use things like aluminium and a similar group 3 element, as we are going to see. Now, the p-type semiconductor, as I told you, we use group 3 elements to create p-type because of what? Lack of one electron, which creates the hole. And examples includes boron, aluminium, gallium, and indium. They are all group 3 elements, and they can be used as what? Acceptors in impurity doping. And any atom that uses this one as impurities, you know, it has one place requiring an electron, and we call it what? A p-type, because we have excess positive charge. And the atom shares it 3, as I have already explained, and 1 is leaving without, or is left without any pairing, and that is why we have p-type semiconductor. And this free hole can exist even at room temperature or below room temperature, because the hole is there without breaking of any bonds. Therefore, we say the holes are the majority. That is why we said in p-type semiconductors, holes are the majority, electrons are the minority, and vice versa. So after understanding the process of doping and knowing that we dope either group 5 or group 3 element to have p-type semiconductor or n-type, now we are going to look at a law. We call it mass action law, and it talks about carrier concentrations. And what this law is saying, you know, if you introduce group 5 element, you have what? N-type semiconductor. And if you introduce group 3 element, you have p-type semiconductor. But what the law is trying to tell us is that under the thermal equilibrium, for any semiconductor, either it is p-type, either it is n-type, either it is pure, the product of the number of electrons and the number of holes is always constant. That is, if you multiply number of holes and electrons in either p-type, n-type, or pure, it will give you a constant value, and this law we call it mass action law. Now, based on what we have seen, we know even without any introduction of impurity, when the bonds are broken, we have our holes, which are p positive, we have our electrons, which are negative, and when I introduce group 5 elements, now I have donor. This is ND, the number of charge carriers as a result of what? Group 5 introduction. And here Na stand for acceptors. That is when I dope a pure semiconductor with group 3 elements. So let us assume the charge density is given by this letter, that is rho. Now the total charge concentration or charge density is given by this formula, rho equal to Q, which is electron charge, into P minus N plus Nd minus Na. But if we reach equilibrium condition, this rho becomes equal to 0. And if it is equal to 0, equating everything here to 0, I can say divide both sides by Q, meaning I will be left with only what is inside the bracket. And you can see rearranging these ones will give me this, N minus P equal to Nd minus Na. And we have already seen that if we are dealing with pure semiconductor, my Nd, that's concentration of donor, and my Na, concentration of acceptors, should be equal to 0, because we didn't introduce any foreign material. So for this, if these two are equal to 0, it means my N is equal to P. And if you can remember, in our lecture number 1, that's what we said. In pure semiconductors, the number of electrons equal to the number of holes. And we have seen this formula that says their product N times P is equal to Ni square, where Ni, I told you, is what? Intrinsic concentration. So let us assume now we are dealing with the N-type, that is, we introduce group 5 elements. Then I have my donor concentration will be very large, and my acceptor concentration should be 0 because I didn't introduce group 3. So if acceptor concentration is equal to 0, coming back to this place, I will say N minus P is equal to Nd because Na has gone to 0. Now, under this condition, I can now say from here, since I am dealing with what? Donors, group 5 elements. Now, the concentration of my holes, because I'm dealing with what? N-type semiconductor. The concentration of the holes should be very, very, very small because it is the minority carriers where electrons are the majority carriers. So I can say approximately, if this P becomes equal to 0 or approximately 0, my N is approximately Nd. Now going back to this, my formula, wherever I see N, I will substitute it with my what? Donor concentration. And doing that will give me P equal to Ni square all over N. What am I doing? I'm trying to find the concentration of the minority carriers in what? N-type semiconductor. Following the same analysis, I can find the concentration of the minority carriers in what? P-type semiconductor, which is what? Dealing with the acceptors. Now, if we understand this from those equations we have seen, I have established the formula for calculating the majority carriers in P-type and what? And N-type. And what they are telling us is that the concentration of these minority carriers, they depend on the level of what? The impurity we introduce. Here is my donor concentration is very, very large. Since this one is constant, this should be small. But if it is small, this one should be big, and also here. And one thing we should know, which is very, very important, is that the very small amount of doping, that's the impurity we introduce into the pure semiconductors, it has effect in only changing their electrical conductivity, but they don't have any effect on their chemical or mechanical properties. It only changes their conductivity by increasing it. And we have already seen the intrinsic concentration is equal to the concentration, which is 1.6 times 10 to the power 16. Now the next thing is the transportation of electric current. As we know, the charge carriers, when they exist freely in any conductor or semiconductor, they move from one point to another. So what is the formula for calculating their speeds? We have what we call the drifts, and we have what we call diffusion, as I've already explained in the first lecture. Diffusion as a result of temperature, drift as a result of application of what? Electric field. So if you have any temperature that is above 0, that's absolute 0, definitely there is kinetic energy that causes the molecules to start vibration, which brings about their breakage. And if they break, definitely they will be moving randomly, and anything that is moving can what? Have a speed. And the formula for calculating the speed, Vth, is equal to square root of 3 kT all over m. We put asterisk on it. K, Boltzmann's constant, T, temperature, and m is the effective mass of the carrier. Is it a hole, is it electron, whatever it is. So if we understand this, we now come to the drifts in an electric field. I told you, whenever electric field is applied to a substance, it will disturb its equilibrium because the molecules get more energy. Anything that is disturbed, definitely it will start moving, and it will be accelerated by the amount of electric field applied to it. And when this started happening, this energy due to electricity will be complementing the energy due to temperature. And as a result of this, we have what we call a drift, combination of the effect of what? The temperature and the electric field. And a condition is reached when the velocity becomes uniform. It moves with a constant velocity, no increase, no decrease. And in this uniform velocity, we call it a drift velocity, which is directly proportional to the electric field applied, but it is moving in the opposite direction to the what? Electric field. If electric field flow in this direction, the other one should be in the opposite. Now, the formula for calculating the drift velocity VH for the holes is equal to mu HE, where mu H is what? The mobility of the hole, where this is what? Electric field intensity. And mu E here, VE is equal to mu E for the electrons. And as we have said, this mu stands for the mobility. Therefore, the mobility of the holes is given by this 0.045. And the mobility of the electron is 0.135. We can see that that of electron is bigger than that of hole. So from this, we can say, let us assume that we have Q as the charge of an electron, and let's say N over T is the number of electrons passing a region per unit time. Now, we can remember that current is equal to total charge all over time. And if Q is the charge of single electron multiplied by N, that's total number of electrons, that will give me my total charge all over time. And also, the charge density is equal to the amount of current, that's current density J is equal to the amount of current all over what? Cross-sectional area. But wherever I see this, I am going to substitute NQ over T. So putting it here, I'll have NQ all over T. But where is my T? Look at what happened. You know, this A is here, but the time is always equal to velocity all over what? Distance, because you know the velocity of anything is equal to total distance moved all over what? Time. So therefore, if you now say this V stand for the volume and this L stand for what? Length. You know, volume over length should give you a cross-sectional area. Just take something like a cylinder. The formula for calculating the volume of the cylinder is pi r square h, where pi r square is the what? Area of the circular part, and the h is what? The length. Now, if we assume this N, that's the total number of electrons, A cross-sectional area, L is the what? Length. I told you the length and the cross-sectional area is equal to volume. Here I have total electrons all over what? Volume. And we represent it by a small letter representing number of electrons per unit volume. So wherever I see N over LA here, I'll remove it and put small n. And doing that will give me NQV, ampere per meter square. But we have seen previously that the velocity is equal to mu E. That is mobility times what? Electric field. Now, wherever I see this V, I'll represent it or replace it by what? Mu E. And that will give me NQ mu E. Okay. And if we understand this, we now go to what we call electric conductivity. The conductivity of any material is equal to NQ times mu. That is N, charge per unit volume, Q, the charge of electron, and mu is the mobility. It can be of electron, it can be of hole. If we go back to the Ohm's law, we know that resistance is equal to voltage over current. And we also know the resistivity of a material is always reciprocal of its what? Conductivity. Therefore, I can say conductivity is also reciprocal of what? Resistivity. Now, we have this equation standing for my what? The current density. Now, if I come here, I can say for the holes, I have Q, P, where P is representing this N, because N is the what? Electrons per unit volume, and P is now what? Holes per unit volume. And mu H is this mu, this is for the hole E, and this is for the electron. What we did here, we derived the formulas for calculating the current density in what? Holes and in electrons. Now, if you want to find the total drift current density, all you need to do is to add the two, that of the holes, which is this, and that of what? The electron, which is this. If you look at this, Q are common and E are what? Common. I can factorize them out, Q and E. Then inside I have P mu H plus N mu E for electron in the hole. Now, this is my current density. But the conductivity, I have already defined it from here. See it, my conductivity is equal to NQ mu, meaning the conductivity is equal to that of the hole plus that of the what? Electron. You see, if I expand this, this will be QP mu H for the hole, and here should be what? NQ mu E for the what? Electron, adding the two. But if you are dealing with a pure semiconductor intrinsic, your N is equal to P and is equal to what? Ni. So I'll come here, wherever I see N and P, I'll remove them and put Ni, and if I factorize it, it will be here Q and I. Then we are left with their mobilities inside the bracket. And if you are dealing with the extrinsic, that is the dot, we are not going to remove this P and N, we leave them as they are. Excuse me. So therefore, for the N-type semiconductor, this is my conductivity, and for the P-type semiconductor, this is my conductivity. Now, understanding this, we go to the effect of the temperature. We have already explained, if you have a pure semiconductor, whenever the temperature rises, the bonds start breaking. Whenever the bonds are broken, charge carriers are produced. When charge carriers are produced, the resistance is then decreasing, because the more the conductivity, the smaller the resistance. Therefore, more electrons are breaking from their covalent bonds. Whenever the temperature is increasing, they move from the what? Valence band into the conduction band. If you are dealing with a pure metal, already the electrons are free, they are in the what? Conduction band. The only thing that happens is that whenever temperature increases, they will start vibrating randomly, and when they are vibrating randomly, they will be colliding with one another. Instead of increasing their conductivity, it is going to what? Decrease. So we are saying in pure semiconductor, rise in temperature brings about increase in conductivity, but in metals, rise in temperature causes decrease in conductivity because of the collision and increase in their resistance. And if you are dealing with the impure semiconductors, the ones that are doped with either group 5 or group 3, we know that their conductivity increases with what? Increase in temperature. And whenever you reach a point that we call critical temperature, the number of your holes should be equal to, almost equal to number of electrons, and that is repeating the mass action law. So at this point, our extrinsic semiconductor is now going to be behaving like what? Intrinsic, because the number of holes is equal to number of what? Electrons at that critical temperature. And this temperature for the silicon requires this amount of energy, and for the germanium it requires this. Can you see that this is 0.05 and here is 0.01, meaning that of silicon is 5 times that of what? Germanium. The next thing is, we have already explained how P-type semiconductor is produced by doping with group 3, how N-type semiconductor is produced by doping with what? Group 5. Now we come to formation of P-N junction devices. The basic one is a diode. And how do we form a diode? All we need to do is to get our pure semiconductor. It can be germanium, it can be silicon, and we dope it with group 5 elements. It will give us N-type semiconductor. And we get another one, we dope it with group 3 element, it will give us P-type semiconductor. And if you join these two, they will give you P-N junction, because one is N-type, the other one is P-type. But in reality, this is not what is done. All we need to do is to get a material, pure semiconductor, silicon or germanium. On one end here, we introduce group 3 to give us P-type. On the other end, we introduce group 5 to give us N-type. And this will give us our P-N junction. And this is the symbol. This point where we have our P-type is the anode, and where we have N-type is the cathode. So this is explanation of all what I said. When P and N-type are connected together, they will give us P-N junction diode. And you know, the free electrons and the free holes, they will now be migrating across the junction here. Here I have free electrons, here I have free what? Holes, and they will be migrating across this. What happens when positive and negative comes together? They will recombine and neutralize each other. So as time goes, the recombination takes place, and here it will be a region where we don't have any pre-charge carrier, and we call it a depletion layer. So when this depletion layer exists, when this depletion layer exists, so we have a region where for you to push electrons from N-type to cross, you need to apply a negative voltage. For you to push holes from the P-type to cross, you need to apply what? Positive voltage. And therefore, they now have this gradient, positive on this side and the negative on the other side, as you can see here. this is my p-type end, and from this end, this is my depletion region where the recombination takes place. So for me to push these holes to go to this direction, I have to be applying positive voltage rising like this. And from here, my n-type, for me to push electrons into the other side, I have to apply a negative voltage falling in this direction. Now, how do we construct a diode? As I have said, we don't use different p-type material, different n-type material, and join them. What we normally do is to get single semiconductor material. At one end, I inject group 3 element. At the other end, I inject my group 5 elements, and therefore this side will be P and the other one should be what? N. And we have already seen the group 5 elements that are normally used. They include things like this gallium arsenide. Sorry, this one is a compound semiconductor. I have already discussed it in my first lecture. So as I have already said, in this region, that's the depletion region, we have no charge carriers at all, but in reality we do have some small value of charge carriers, and these ones, they are the minority I have in the p-type, which are holes, electrons, and the minority I have in the n part, which are the holes. They are the only ones that exist. So therefore, whenever this minority are crossing the junction, they create a current, and we call that current diffusion current, and sometimes we call it reverse saturation current. So if we understand this, the next thing to do is the biasing a junction. By biasing, we mean to apply external voltage in order to allow the conduction across the junction, or to prevent the conduction across the junction. And for me to explain this, let us look at these diagrams. Look at the first one. This is my PN junction. I didn't apply any external supply to it, and as I've already explained, due to the combination across this junction, I'm going to have depletion region. But here I now apply, let's say this is a battery, the positive go to the P and the negative go to the N. You know, this P will be pushing electrons away like charges repel, and this negative will pushing electrons toward the junction. So as they are coming closer to the junction, the width of my depletion region will be reducing until when it is closed. The moment it is closed, now the current will start flowing, and this is what we call forward biasing, positive to P, negative toward N. But if I want to reverse bias it, I'll just change the polarity of the battery, my negative to P, so that it will be pulling the holes away from the junction, and my positive to N, it will be pulling the holes away from the junction. So instead of reducing the width of the depletion region, it will be widening it, and in this case, no conduction across the junction. Therefore, what we are saying here is that if you have a PN junction diode, you can supply electricity to it in such a way that it will be conducting, and that is forward bias. You can apply electricity to it in such a way that it will block the conduction, and that is what we call a reverse bias mode. And these are what I have already explained. I said the positive pole to the P, the negative to the N type, and for this they will push electrons and the holes closer to the junction, closing the depletion layer, and at the end of the day the conduction will take place. And in the reverse direction, we said we apply the negative to the P and the positive to the N, so that it will draw the holes and electrons away from the junction, thereby preventing the conduction. And the amount of current that we expect to flow if it is forward bias is given by this I equal to ID, that's the total diode current, minus IS, which is my reverse saturation current I have already mentioned. The reverse bias modes I have already said, the negative terminal of the battery go to the P side, and the positive terminal of the battery go to the N type. Therefore, the holes and electrons are attracted away from the junction, and if that happens, the depletion layer will become very wide, and if it becomes wide, it means no any conduction across the junction. And I told you, even in this condition, we have minority carriers which are crossing. Once they are crossing, they bring about creation of a current which is very small, and we call that current reverse saturation diode current. So the characteristic curve of the diode is like a graphical representation of how the current flows when voltages are applied to the diode. Here is my vertical axis representing the current, and here is my horizontal axis representing what? The voltage. Now it is saying that when you start increasing the voltage from 0 to some positive value, still the depletion layer is there and no conduction, until when you reach a minimum amount of voltage, we call it VC. That is when we are forward biasing, and this is the minimum amount of voltage to completely close the depletion region so that electrons and holes will start crossing. The moment you reach this, as you increase the voltage, the current will be rising exponentially, and this is the formula: ID equal to I0, which is my reverse saturation current, exponential VD, which is this voltage we apply the positive, all over what? N VT. This N is a constant, VT is my threshold voltage. And in the reverse direction, when you are reverse biasing the diode, you are widening the what? The gap. That's the depletion region. As it is widening, no current will flow. But I told you we have minority carriers, electrons in the P, holes in the what? N. They will now be crossing, and because of that they are crossing, you can see this amount of current, very small, flowing in the opposite direction. I will call it reverse saturation current. So gentlemen and ladies, this is the end of the lecture number 2 of this course. I advise you to watch it and watch over again. Whenever you have any problem while watching this thing, you can meet me for clarification. Thank you very much. We will meet in the next lecture, God willing.